Welcome to the fourth video in this first class session. We'll go ahead and hopefully finish Huns Rule and an introduction to the Lewis bonding model. I used to teach in Lewis 1 at Berkeley, where he was based for a while, as he made up his bonding model. Anyways, Huns Rule is that you need to make half-filled orbitals first when you encounter degenerate orbitals, and that's because placing electrons in different degenerate orbitals is a lower energy condition than placing them in the same orbital at a given level. And it's lower energy because the electrons are in literally a different space, so each of them feel less repulsion from the other. And so carbon, for example, the ground state electronic configuration, we would place 2 electrons in the 1s orbital, followed by 2 electrons in the 2s orbital, and then we place 1 electron in a given 2p orbital and the other electron in another 2p orbital of the 3 possible 2p orbitals that we have for carbon. The valence electrons are the most important for bonding. The number of valence electrons equals the number of electrons outside of a closed shell. So for example, how many valence electrons does carbon have? Well, our closed shell is the 1s orbital, and so there are a total of 4 electrons in the n equals 2 level, so carbon has 4 valence electrons. So we'll go ahead and move forward to the Lewis bonding model circa 1916 or so. And this is based on the idea that atoms will react so as to form a closed shell of electrons. The Lewis assumption, or the Lewis postulate, is each atom in a bond will attempt to gain or lose enough electrons to achieve a closed shell. For example, we might consider fluorine. Each fluorine atom has 7 electrons. We're 1 short of a closed shell because the n equals 2 energy level can hold 8 electrons. Hence we have an octet rule. And here we have our 2 fluorine atoms coming together, and we can see that 1 electron from the fluorine atom on the right is sort of being drawn to go and meet another electron on the fluorine atom on the left with these half-headed arrows. Wow, half-headed arrows. They describe single electron movement, and we always start with the tail of our arrow from the electron and the head pointing to where it's going. So of course, if we have a single fishhook arrow, we're describing moving only that 1 electron that the tail of that fishhook arrow begins at. And if I follow this symbolism correctly, what I'm doing is I'm using those 2 electrons to form a bond between the 2 fluorine atoms. So I write a line connecting the 2 fluorine atoms. In that line, there are 2 electrons. Sometimes we don't draw all the lone pairs on our atoms. We assume that you know how many lone pairs a given atom will have based on its position in the periodic table. So that's something that you might need to practice. A reaction arrow is sometimes drawn as simply an arrow. No reaction arrow is an arrow with X through it. That kind of makes sense. What next? Oh, here's a symbolic representation of a covalent bond, which you might expect to find between 2 fluorine atoms. You can see that the fluorine on the right has this dashed sort of grouping of electrons, and wow, it's sharing one of the electrons from the fluorine on the left, so it has a total of 8. And the fluorine on the left has this solid line indicating its group of electrons consists of 8 entire electrons, where it's also sharing the electron that belonged to the fluorine on the right. So in these covalent bonds, electrons are shared. In the case of diatomic fluorine, the covalent bond is nonpolar. What do I mean by nonpolar? So each fluorine pulls with the same strength, so you're not going to set up a more positive or more negative end on your diatomic fluorine. It would be incorrect to represent the diatomic fluorine bond as ionic. In that particular condition, you might say, oh, the fluorine on the right possesses all 8 electrons, and we have to give it a formal negative charge because 7 electrons would be the neutral valence form of fluorine. And we'll go into deeper depth on how to assign formal charges if this is confusing. The fluorine on the left is drawn with only 6 electrons, whereas we know fluorine should be neutral with 7 valence electrons, so we're missing 1 electron, so we have to give it a formal positive charge. In the ionic sort of sense, there is greater charge separation than you would find in a polar covalent bond or even a nonpolar covalent bond. So examples of ionic bonds may be lithium fluoride. So you could envision reacting lithium metal with fluorine gas to create lithium fluoride salts and heat. It's a very exothermic reaction. In this case, electrons are not shared. We could go ahead and write a theoretical reaction scheme in which lithium is giving up its single valence electron to fluorine, and you would have to give lithium a formal positive charge and then fluorine, of course, a formal negative charge. Similarly, you would expect the same sort of thing with beryllium fluoride. So beryllium could react with diatomic fluorine to form beryllium difluoride. So your beryllium has a formal 2+ charge, and each fluorine has a formal negative charge, so overall neutral. Magnesium and oxygen also react. Here we go with 2 magnesium solid and diatonic oxygen, and we're forming a total of 2 magnesium oxide molecules. And so we could symbolize this as magnesium with a pair of valence electrons donating them to the oxygen, and we will in result have magnesium with a formal 2+ and an oxygen with a formal 2- charge. And we use a double-headed arrow in this case to represent 2 electron movement, and notice that the arrow begins where the electrons start and points towards where they are going. What is a covalent bond? Well, in diatomic fluorine and diatomic hydrogen, etc., there is a pure covalent bond, which is nonpolar, no dipole. We could take chlorofluoride as another example, reacting chlorine with fluorine. And here we get a dipole. Fluorine has the greatest electronegativity, so it pulls the hardest on electrons in a covalent bond. And so fluorine is pulling harder than chlorine, so we draw these dipole arrows to suggest that chlorine has some delta positive characteristic and the fluorine has some delta minus. And electronegativity is sort of a measure of an atom's attraction for electron density. Here are some electronegativities of common atoms that we might encounter in our study of organic chemistry. Hydrogen has 2.2. That's kind of high for an element on the left side of the periodic table. Most metals are low, like lithium and beryllium, 1 and 1.6. And we're increasing in electronegativity as we go across this row. Boron is 2.0, carbon 2.6, and we're steadily increasing to when we hit fluorine at 4.0. As we go down a column, our electronegativity is decreasing. So we go from fluorine at 4 to chlorine at 3.2, bromine at 3, iodine at 2.7. There are reasons for these trends. As we go across a row, we're increasing the positive characteristic nucleus, the number of protons in the nucleus, and we're keeping the electrons in the same atomic orbitals, so they're being pulled closer and closer to the nucleus, and so we're increasing in electronegativity. As we go down a column, we get higher and higher energy levels, and so there is more shielding of interior electrons that sort of reduce the positive charge that those valence electrons feel, and so we get lower and lower electronegativities. Predicting covalent versus ionic bonds, we look at an electronegativity difference delta. Of course, for diatomic fluorine, our difference in electronegativity is 0. For chlorofluoride, it's 4 minus 3.2 or 0.8, so we would describe that as a polar covalent bond. In general, delta of 0 is a nonpolar covalent bond. A delta of 0.1 to 2.0 is polar covalent, and delta is greater than 2.0 we would generally describe as ionic. And so that pretty much completes this last video for our first class. Thank you for making it to the end.